Recordings rolling. It is Tuesday, April 22nd. Yesterday, we started a new topic, theory of relativity. So, I'll recap what you guys saw yesterday, do a little review. And then there were some ideas I didn't even get to. So, mass energy equivalence, general relativity, I'll go over those. Global positioning system, GPS. You guys use your phone to navigate around town. That only works, or at least we only understand why it works, using theory of relativity. So, I've got a video for you guys on that. And then about the last half of class, about last 25 minutes or so. Oh, I have some puzzles for you guys, so we're working towards that. Be there later today. All right, so story starts about here. Things good. Start story is the first time that the speed of light was accurately calculated was before the Civil War, so 1849. And the story goes like, oh, by the way, the puzzle I have for you guys today is basically this puzzle, except backwards. So, recap the story here. Now, guys, pay close attention to the story. If you follow the story, then that's going to make the second half of class a lot easier. So it goes like this. I have some light source I'm representing with a candle. I have some mirror several kilometers in the distance. And here's an observer I'm representing with an eyeball. Now, this observer can see the reflection of this light source in the mirror. Okay? Let's also throw this cogwheel relatively close to the observer. And let's give it a spin. Now, if this cogwheel is spinning fast enough, then some of these light rays that are hitting the teeth never reach the mirror to begin with, so you don't see the reflection. But whatever light rays go through these gaps and come back to at the same location, if there happens to be a tooth in the place of where a gap used to be, just a fraction of a second earlier, then the observer doesn't see that either. Okay. And what that looks like from the point of view of the observer is if this light bulb represents the reflection, and you spin this wheel a little faster, that's this omega, isn't it? Some angular velocity. Okay. Then if you get it just the right angular speed, just the right omega, then it's going to look like a door is closing on that reflection. And right at that moment, if you know exactly what omega is and you know the distance to the mirror, there's enough information lying around, you can calculate the speed of light. Here's the math. So it got some middle equations in green. And then this gold box equation will tell you the speed of light from all those numbers. Okay? So hold on to this idea. You will see this about the last half of class. You guys are going to be thinking really deeply on this puzzle. I want to see if you guys can solve what Fizeau solved back in the day. Okay? Now, take this. Now we know the speed of light. Let's fast forward a few decades. So you got these guys, Michelson and Morley, thinking, well, we know that sound travels on a medium, like air, for example. So we know light's a wave or has wave properties. That's probably also the case. What would Earth's speed be relative to this luminiferous ether, we're going to call it? Okay. So they set up this experiment. And oddly enough, it didn't matter the orientation they had. If they had light going east-west or north-south. You guys remember those two guys paddling in the boats yesterday? One guy was in a river, one guy was in a lake that's sort of analogous to or going east-west, north-south. Right? Of course, the Earth is spinning. If they just morning or night, or there's revolving around the sun. What about winter versus summer? It didn't matter. They always got the same speed of light regardless, which was weird. That's why, so they unintentionally disproved there being any kind of luminiferous ether. That's why to this day, you guys remember a question from last week? What form of heat transfer can happen through the vacuum of space? And to this day, you guys say light waves can travel through the vacuum of space. Electromagnetic radiation can travel through the vacuum of space. That comes from this experiment. Now, Einstein was looking at this, and he realized that they were setting up a conundrum here. That I think a lot of people were kind of seeing, like, no, okay, that's kind of interesting. But Einstein thought really, really deeply about this. He said, hold on a minute. That means if you have somebody, say, on a train moving at a relativistic speed, close to the speed of light, or later on, do you guys remember the twin paradox? I might call this guy rocket twin with the red hat and call this guy earth twin with the green hat, right? That these two guys would see the same beam of light travel different paths. So inside the train, you see it go up and down, but outside the train looking in, you see it travel on a diagonal. But both of these guys would perceive the same speed of light. That's the result of this Michelson-Morley experiment. So if they break out a Fizeau cogwheel and they do the experiment, they both get the same speed of light. Okay. And what Einstein said then, see if you guys remember this from yesterday or can figure this out. If these two guys see light travel a different distance, but they calculate the same speed, they must be perceiving different what? Times. Hence these clocks. Right? So if you're a rocket twin, I'll call this guy rocket twin, right? Then time beats slower for you, and if you're earth twin, time beats faster for you. Now, I should emphasize, in your own locality, you notice nothing strange about your own clock. But if these two guys have telescopes and they're looking at each other's clocks, then earth twin sees rocket twin's clock going tick tock, like really slow. And rocket twin looks back at Earth twin's clock that looks like it's going really fast. Right? There's some relativistic speed. Now you can set up a Pythagorean theorem based on this triangle geometry right here. Here's your Pythagorean theorem setup: a squared plus b squared c squared, and you can rearrange it and get Earth twin's time in terms of rocket twin's time. And you have to divide by the square root, which is called the Lorentz factor. You guys see that? Okay. And the faster the train or the rocket goes, that would be embedded in the speed. The speed of light is a constant, that's c, right, which we got from Fizeau. Right? It's all there. You saw that? Okay. Now, if you think about it some more, I'm going to say, well, if these two guys disagree about how much time has passed, suppose you went on some interstellar trip in a rocket. You're going to send this guy in a rocket, so several light years out to some destination planet. It's like 10 light years out. Okay? But if they disagree about how much time has passed to get there, they must also be disagreeing about the length of the trip itself. So that leads to another dilation. I'll call it a length contraction. So we got this top one from Einstein's train geometry, Pythagorean theorem, right? Earth twin, rocket twin time, twin paradox. Okay? But this length contraction also has to fall out of that to be consistent with that. Do you guys remember yesterday the train going through the tunnel, the train paradox? Right, so are both ends of the train sticking out, or is they completely enclosed in the tunnel? But it depends on your frame of reference if you're inside the train or not. And both are correct. There's this relativity and simultaneity. Right? Now, a third dilation that also happens is momentum dilation. Later this week, you're going to see a puzzle that involves this. Scientists at the Large Hadron Collider over in Switzerland run into this all the time. They throw some hydrogen in the synchrotron, it spins around at 99.9 something percent the speed of light, and they use magnets to steer it. But they have to increase the magnetic field strength because it looks like there's way more mass than they put in. Why? Because of this dilation effect, because you're divided by this Lorentz factor. Now, these are equation form. You can also turn each of these into graphs. So I have one of the graphs right here. So for momentum is a function of speed. And notice you're running into this limiting speed of light. That's what c is. Okay? And how does Einstein physics compare to Newtonian physics? Well, as long as you're moving at a non-relativistic speed, say less than 10% of the speed of light, you guys see that those two pretty much agree. It's pretty much a match. Okay? But if you move at a relativistic speed, so get closer to the speed of light, these two diverge. So momentum, Newton said momentum is just mass times velocity. You guys remember collision carts from last semester? Einstein says, well, it starts out being approximately true. But at relativistic speeds, you have to divide by the Lorentz factor. In fact, you can never reach the speed of light. The closer you get to the speed of light, your momentum would approach infinity. Again, if you're along for the ride with rocket twin, you never notice anything strange about your own mass. But somebody outside this, like an inertial, so an observer in an inertial frame of reference, so let's say Earth twin, would notice this happening. So scientists at the Large Hadron Collider see the massive hydrogen go. Okay, right? You can do the same thing for time and for length looks a little bit different graph, but for time. Now, an interesting consequence of this is that from the point of view of photons, you can make a good case that photons perceive there to be no space and no time in the universe. So that's interesting. Minkowski's space-time diagram. So right now we are at the center right here. I have a couple of spatial axes and basically a time axis going vertical. You can think of it that way. So speed of light times time, comparable to the other two. Okay? And you can think of time beating forward. So past, forward, moving basically up here as time moves forward. You guys see that? Okay? So we're all right here at the center. Okay? And what could ever affect you has to be in this cone that's labeled past. And however, whatever you can affect in the future has to be in this cone labeled future, where this red dashed line marks the borders of that cone, because that would be light physically traveling, right? So, for example, could you send an email to Mars in the next 2 seconds? No, because it's too far away. Light can't reach Mars in the next 2 seconds. So that may be like a point like way out here, right? So that'd be impossible. Or if some explosion happens on Mars right now, are we going to know in the next 2 seconds? No, because that could be like a point down here. Now, we might know several minutes from now. Maybe it's breaking news in an hour. There was a massive volcanic eruption on Mars, right? But we wouldn't know that until that information reaches us. All right, so that takes some time, right? All right. Next, also out of special relativity comes this equation, mass energy equivalence. Now, there's a whole proof that leads up to this. I just have the last couple of steps here. I know everybody's seen this in their life. You guys have all seen this equation, E equals mc squared. Okay. I bet most of you guys know what these variables stand for. You guys tell me, guys, what does E stand for? Energy. What does M stand for? Mass. What does C stand for? The speed of light. Okay. Now, speed of light is already a crazy big number. It's like 10 to the 8 meters per second. If you square that, that's 10 to the 16, and 3 squared is 9, so almost 10 to the 17, and then it's got some units, right? Which is so big that I'm just reporting it as a power of 10, 10 to the power of 17. Oh, this right here This is the energy of nuclear reactions. Nuclear reactions. Are you guys ready to talk about nuclear reactions? Right. So let's rewind about 100 years in history. Go back 100 years ago. There were some fission reactions happening. Now, here's one really common fission reaction. If you take one particular isotope of uranium called U-235, now most uranium is U-238, but if you can separate out the U-235, about 1% of that, right? Of all uranium, about 1% of it is U-235. If you bombard that with a neutron, it can split into smaller atoms, and a really common reaction is it splits into barium and krypton. But if you add up all the mass of all these reactants, post-nuclear reaction, and you compare that to the mass of the original U-235, guess what? There's missing mass, which is weird. You guys remember taking that whole class chemistry, and there was that principle called conservation of mass? Every single chemical reaction you ever did, every lab you ever did that involved a chemical reaction, mass was always conserved. You guys remember stoichiometry and all that? Okay. But when you get to nuclear physics, that's no longer the case. Okay, so if you make a graph of binding energy per nucleon as a function of mass number, graph looks like this. There's also another version that looks like upside down to this, a little bit different perspective, right? But the fact there's a height change is also consistent with that. So if I take this uranium and I split it to say krypton, barium, which are somewhere in here, there's a difference in energy and a difference in mass, and that is linked by this formula right here. So if you account for the missing mass, multiplied by the speed of light squared, that tells you how much energy, say, in joules you can get. Later this week, I'll have you guys do the calculation. You're going to see how much crazy amount of energy that is. It is an enormous amount of energy. Okay? Did you guys learn in history class something called the Manhattan Project? You guys know that one? Right. So World War II kicks off. The Allies and Axis powers realize, the Allies, since we're on that side, are worried. What if the Axis powers get hold of this nuclear technology before we do? That would be really, really bad. So the U.S. government pours an enormous amount of money into fast forwarding this particular research. Right, so by 1945, we get the first atomic weapons. Now, the two bombs that we dropped on Japan, one of them was a uranium bomb, another one's a little bit different one, is the plutonium bomb, but they're both fission bombs, both fission process, right? And all the power plants we have today, all the nuclear power plants are some version of fission power plants. Guys, right now in this room, the lights, the air conditioning, the projection right now, approximately 20% of that is from fission reactions, right? Which is could be uranium, could be plutonium. There's also a thorium process, which is not widely used, but there are advocates for using thorium, the number of advantages that that has. Okay? Now, what about the left side of this graph? Because do you guys see this jump from hydrogen to helium? You guys see that that's way, way bigger than breaking apart uranium into these other smaller ones? You guys see? It's a much bigger jump. It's several hundred times bigger, and you can round it up to about 1,000 times as much. So if you take a couple of hydrogen atoms, and I have some isotopes here. So I have deuterium and tritium. So that's hydrogen with an extra neutron and hydrogen with 2 extra neutrons. Okay. And you fuse those together, then you get approximately 1,000 times the energy that you do from one of these fission reactions. Now, the first time that people did that was back in the 1950s. So the United States and the Soviet Union, about the same time, I think the States was first, figure out how to create a hydrogen bomb. So it's also called a thermonuclear bomb. Now, that thermonuclear bomb has never been used in war, unless you consider the Cold War, right? So just experimental. Right? Now, have we ever taken this fusion reaction right here and turned this into a power plant? We're working on that. So that's a developing technology. So it's not quite there yet. There's a joke in science that fusion power plants are always 20 years off, right? 20 years away. Right? So hopefully in our lifetimes, though, because the sources of energy that we're using right now, well, there's always trade-offs and there's downsides. So fossil fuels, we're going to run out of them, and they're polluting the environment like crazy anyway. Solar and wind are nice, but it's kind of hard to get the energy density, the amount of energy we need out of those, right? But the ocean is full of deuterium and tritium. So once we crack this puzzle, we'll probably have plenty enough energy for whatever we could imagine that for the foreseeable future. Okay? So there you go. There's energy of nuclear reactions, and the equation that pairs with that is E equals mc squared. Right? Okay. Now, this is all special relativity that Einstein publishes in 1905. Fast forward in time to about 1916. Einstein also incorporates gravitation to this model of relativity. And that's what general relativity means. Right? So it means we're also incorporating the effects of gravity. Right? In fact, Einstein's picture of gravity differed from Newton's picture of gravity. Now, if you look at Newton's picture of gravity, you guys remember gravitational force equals gmm over r squared? You guys remember that one? That equals gmm over r squared. See if I can Here it is. I got a poster for that right here. So here's how Newton said that gravity worked, or at least he could quantify it in this expression. So there's a gravitational force between the Earth and the Moon. Give the moon a tangential velocity, and this force acts as a centripetal force and holds it in orbit. That's what Newton said, right? But why does this work? Nobody knows, right? But Einstein says, oh, I think I know. I think that this is actually an approximation for a different phenomenon, which is that masses warp space-time. So if you thought about space-time being a fabric, like a four-dimensional fabric, 3 dimensions of space, 1 dimension of time, mass is going to warp that. So if you send the moon at some, tangential velocity nearby the Earth, the moon is only, this is according to Einstein, the moon is only ever following a straight line path, but it's a straight line path through curved space-time. That's why to us it looks like the moon is orbiting us. Straight line path through curved space-time, right? Same thing between the Earth and the Sun, something like that, right? And what is this good for? Well, if you take Newtonian mechanics does fall short in a number of places. For example, if you look at the orbit of the planet Mercury around the sun, it does not exactly align to what Newton and Kepler said it should do. It's a little bit of discrepancy. Nobody could figure out for a long time. Einstein said if you follow these formulas here, and there's different versions of this, I included the one that also includes dark energy, which we'll talk about by the end of this week, that more accurately shows the orbit of the planet Mercury and all the orbits, because this actually simplifies to Newtonian mechanics for non-extreme cases, right? So we got now. Newtonian mechanics is all you need to run the Apollo program to get to the moon and back, right? But if you want to do some extreme physics, figure out, say, what's going on near a black hole, maybe you need something more like this, okay? Now, if you come up with a new theory to replace an old theory, like Einstein physics replaced Newtonian mechanics, you need to come up with some testable predictions that the new theory can explain that the old theory can't, right? And of course, anything that the old theory was pretty good at explaining, the new theory also needs to cover, right? So we need to check all those boxes. Right? So general relativity does simplify to Newtonian mechanics, but it can also explain things that that Newton couldn't. So one of the first testable predictions was this event right here. There was a solar eclipse in 1919. Now, what's special about the solar eclipse is that this is where you can see around the periphery of the sun during the daytime, but the main light from the sun is blocked out by the moon. Right? And it just so happens that the sun has 400 times the diameter of the moon, but it's also exactly 400 times further away. It's just a complete quirk of the universe. So we got, but you guys know that the sun, guys, how massive is the sun in the context of our solar system? Is it half the mass of the solar system? Is it like 99 point something percent of the mass of the solar system? Yeah. How about that last thing I just said? The sun is almost all the mass of the solar system. It's by far the biggest mass anywhere near us. So you should be able to get something of a gravitational lensing effect, where replace the Earth here with the sun. If there was a star behind the sun and you followed a light ray, then the sun should have enough mass to warp that light ray and bend it a little bit. And in the night sky, it would look a little bit out of place. Now, I printed this off my printer, so it doesn't show up super well. I think I see a little tiny star here. But if you Google this image, you'll see the original image. And there's a few stars you can see that you normally wouldn't be able to see during the daytime because it would be too bright. But you can see during a solar eclipse. And Einstein predicted that there would be a gravitational lensing effect if his theory of relativity was true, general relativity. Okay? And he predicted exactly how much each star should be warped out of position in the sky compared to the regular night sky. Right? If you turn this to night and say, where's the stars in the sky? And he was exactly correct. So this was some of the first concrete evidence that general relativity could replace Newtonian mechanics to explain the universe. Right? Here's a more extreme version of that, called an Einstein ring. So this is an actual galaxy. No, if you were nearby this galaxy, it wouldn't look like this ring. It would look like just a regular galaxy. Right? But what's happening here, the explanation is that between this galaxy and us, there's a large pocket of dark matter. Now, dark matter is a little bit mysterious. Nobody knows quite what it is, but it has a huge gravitational lensing effect. Right? So we'll talk about that later this week. And light warps around, a lot like that eclipse photograph, and this galaxy looks like a ring. So it's called gravitational lensing. All right. So let's flip over to GPS. GPS.
Find faster ways down the island. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS. So, exactly how does this incredible tool work?
So imagine you're on a field and you wanted to triangulate where you were. because you know the positions of things in the distance that you can see. By measuring the direction to one object and another object, you can figure out where you would have to be in the field. Well, GPS is like that, but it's larger. It's in all three dimensions, not only where in the field, but how high, and also it's measuring time. You have 4 satellites, they're sending you signals, and you're measuring accurately where the satellite appears to be and when the signals were sent. From that, you can figure out where you are on the Earth's surface.
Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal traveled. The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few meters. To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created. The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day.
After Einstein formulated the theory of special relativity, he went further ahead and he proposed his theory of general relativity, which is not only a theory of space-time, but it's a gravitational theory.
Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds fast every day. This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometers daily.
There you go. Oh, 11 kilometers daily. So, yeah, if you did not account for special and general relativity, GPS would either entirely not work, or you'd have to calibrate the clocks and have no idea why you were doing it. So, GPS will tell you probably within about a meter exactly where you are on the surface of the Earth. And so I just gave you guys each this page. You guys see this page right here? Okay. So we're going to spend the rest of the day looking at this puzzle. Look at Fizeau's Cogwheel. There's a little story here. It's a bunch of questions. I got 7 boxes. I'm going to eventually grade all 7 of these boxes. Okay? Now, look at the other side real fast. There are a bunch of other relativity questions here. Dilation equations. We got mass energy equivalence. So we got a story with rocket twin and Earth twins here. Got some dilation effects. There's a synchrotron. There's mass energy equivalence questions. There's some conceptual questions, and there's some correspondence principle questions. So they're all here. We'll do this a different day this week. Okay. But this side. So back to this side. Just want to look at it real fast. Okay. We got Fizeau's Cogwheel. So I bet this poster could be really handy for the rest of today. Okay. Here, I'll read the story with you guys. So got this Cogwheel, got this mirror way off in the distance. 1849. Fizeau accurately measured or calculated the speed of light spinning a toothed wheel. A beam of light would pass through one gap, and if the wheel is spinning fast enough, then when the beam would be reflected back, that light beam would hit an adjacent tooth. Well, it'd be in the same location because, of course, the tooth would be covering where a gap used to be. Okay? So that the reflection would not be observable by an observer. Ooh. Okay. Now, I gave you guys 4 numbers here. Now, of course, you guys know that his whole goal with this experiment was to determine the speed of light. I'm having you guys do the backwards calculation. I'm giving you the speed of light, and everybody has the same speed of light. So 3 times 10 to the 8 meters per second. I spelled it out to the nearest meter per second. It's like 29979 something. And I'm gonna have you guys calculate how fast was he spinning the wheel. That's your main question you're trying to chase down. So this could be here. Is that Greek letter omega for angular velocity equals some number of radians per second? Is that what you're trying to find? Omega in radians per second. Okay. So if you hopped in a time machine, you could go back and you could tell him how fast he has to spin his wheel. As long as these other metrics are true. I told you guys the distance between the wheel and the mirror. How many kilometers? Notice, guys, notice kilometers. Be careful about that. I have to do some conversions here. I told you the diameter of the wheel in centimeters. And I told you the number of teeth on the wheel, which is just a hard number. Okay? Now, just like normal, you guys know all these papers are different. So my numbers are different from your numbers, are different from your friends' numbers. The only number that's the same for everybody is the speed of light. Okay? Okay, so everybody's gonna have a little bit different spin rate, angular velocity, and so on. Okay? I gave you guys some hints down here. Now these hints are actually just this poster here. You guys remember turntable physics? So like how far as the point of the edge moved has to do with how far the turntables turn times its rail distance from the center. And there's also a speed version of that. So linear speed is equal to angular speed, or how fast rotating times distance from the center. Right? That might be helpful, maybe somewhere along this process. There's actually 3 different ways. I can tell you right now, 3 different ways to get this answer. One way is you can very simply look at this poster, which is hanging from my ceiling right now, and the answer is really embedded in this gold box. Right, so here's the speed of light. It's a function of all these other variables. You guys are trying to figure out this omega, angular velocity. Can you guys do a little algebra shuffle, rearrange that, solve for omega? Okay. There's one way to get the answer. Now, out of these 3 ways to do it, if all 3 methods are converging on the same answer, that's a good sign that you're probably doing everything right. I'm going to grade this whole page, so I'm going to grade all 7 of these boxes. So let's look at these boxes on the right. Because another way to get there is you can follow these simpler questions one by one, and they also lead to the answer in different ways. So what distance does light travel from the wheel to the mirror and back? Woo! Remember, I gave you guys the gap distance, because if you go there and back, what do you have to do with the gap distance? Yeah, you have to double it, right? Because it's there and back. Okay. Also, if I gave it kilometers and I'm asking for meters, do you guys notice that all these units are in base SI units? Right? But the given values might be in kilometers or centimeters. Because how many meters are in a kilometer? 1,000. Ooh, maybe a factor of 1,000. Next question, how much time does it take? Well, if you know the round trip distance and you know the speed of light, because I'm giving you speed of light, so remember you're solving this whole thing backwards. Okay? Can you calculate how much time this whole process would take? Okay? For example, if you were in a car and you were, you guys saw that Jacksonville is a distance of 120 miles away, and you look at your speedometer reading and you're going 60 miles per hour. How much time in hours would that take to get to Jacksonville? You guys get 2 hours out of that? Is that some version of distance equals speed times time? Okay. So next question for you guys. As you're answering these questions going along, make sure that your answers looks approximately correct in terms of order of magnitude. Guys, what would be most reasonable for to pair with this story? Did this box say, oh, it's about 10,000 seconds? Is it about 1 second? Or is it about 1/10,000th of a second? Which number sounds most reasonable? Maybe 1/10,000th of a second. Again, the exact answer is going to vary because everybody's different numbers. But you guys see an order of magnitude idea? Okay. That's really that thought process applies to all of these, and of course, after you graduate high school and go to the real world, hopefully keep this thought process with you. Say, do these calculations seem approximately reasonable? Okay. Next question: how far should the wheel turn so that every tooth covers its adjacent gap? Now, here I'm going to greatly simplify this picture. because throughout today, this has been one of the most common questions I've been getting is how do you approach this question? So all of us have different number of teeth on the wheel, but I'm going to really simplify this down. So let's just get a few teeth on this wheel. Let's get 1, 2, 3, 4, 5. Is that okay? Like 5 teeth on the wheel, just to really simplify this down. Okay. So if during this process the light has bounced off this mirror and back, so going there and back, isn't it true that I want this tooth to have turned to cover the location of this gap during that process? Is that true? And then this tooth covers this gap and so on all the way around. Right? And if you look at the size of that wedge, see, like the tooth started centered on that line, and then by the time the lights bounce back, it's now over here. Right? And I call this angle right here theta, call this theta. Right? For a 5-tooth wheel, which is what I'm doing here for a 5-tooth wheel, just to keep it real simple. Right? Who can calculate theta? Or how would you do that? Well, let's walk through this. So, okay, suppose the wheel made one complete revolution. Now, obviously, it's not going that far, but just as a starting point. Guys, one revolution. How many degrees is that? 360 degrees? Right. Now, for this paper, do you think you want to be using revolutions, degrees, or radians? What makes the most sense? Radians. All right, so let's how about radian? How many radians is one complete revolution? 2 pi. I'm going to jot that down. So I'll say theta equals, I'm going to set up a fraction. I'll go 2 pi, because that's the number of radians for one revolution. Now, of course, it doesn't turn one revolution. So, guys, how big is this wedge? What fraction? What fraction of a revolution is that wedge right there? 1/10. You guys see 1/10? Right? And if you don't see it, then here, let's make a bunch of piece wedges. So I'll go to the center of that tooth, and that gap, and that tooth, and that gap, and so on, all the way around. Right? If you didn't see it before, do you see 10 pizza wedges now? You guys see it? Right. So that's for 5 teeth. Ooh, because if I have 5 teeth, I have 5 teeth, but also 5 gaps. Right? So that's like 10 things, isn't it? Right. So in general, for any number of teeth, I should take my 2 pi radians and divide by what? Double the number of teeth. Right? Do you guys get that? You guys get that? I'm really helping you guys out here just because I keep getting that question all day today. Okay? Right? Really helping you guys out. That to tell you how far the wheel turns in radians. Right? Now, at this point, remember I told you guys that one way to get to the answer is you could just follow this poster and rearrange this algebraically, solve for omega. Right? This brings us to the second way you can also get this answer. Because look at the units. You know how many radians the wheels turned. You know how many seconds this process took. Can you get how many radians per second from those boxes? I think you can. Right? But there's a third way to get it, and that's the rest of these boxes, which I'm also going to be grading. So next question, what's the radius of the wheel? Well, I gave you the diameter of the wheel. Guys, how do you go from diameter to radius? Yeah, it's a factor of a half maybe, right? Oh, no, don't get caught up on this too. You guys see centimeters here and meters here? How many centimeters in a meter? 100. Right? Or how many cents in a dollar? It's also 100, right? How about order of magnitude? Guys, look at the size of your wheel. Everybody has different size wheels. Right? What sounds more reasonable for the number of meters for radius? How about, what if you get 0.14? Or what if you get 14? Or what if you get 14,000? Which of those sounds the most reasonable? Maybe 14, maybe something like that. Right? Again, it's different for everybody, but just think about order of magnitude. Next question, how far would a tooth or gap move during this process? Well, if you know how far the wheel's turned, and you know the radius of the wheel, that's this right here. That's this right here. Do you guys remember this formula? Here's how far the wheel's turned in radians. Here's the radius of the wheel. Here's how far a point on the edge is moved. You guys do that? Next question. What's the linear speed of a tooth? Well, if you know how far it's moved, right? So I could take my ruler and I could suppose I slow down time, right? And measure how far a tooth moved during that process. Probably a few centimeters, right? If you get like a few centimeters, but in terms of meters, you're probably on the right track. And you know how much time that happened in, because that'd be this box right here. Can you get the linear speed in meters per second? Right? Right. And finally, going for the finish, because at this point you'll have all the boxes filled out. But I told you guys there was 3 ways I could think how to get this answer, and I've shown you 2 so far. So that brings us to the third way. if you know the linear speed of a tooth and you know the radius of the wheel, then the connection's right here. Do you guys remember this one? Here's the linear speed of the tooth. That's the last box on the page. Here's the radius of the wheel. Here's the angular speed of the wheel that ultimately you're trying to solve for. And that's the third way you can get omega. Right? So you guys see 3 different ways you get omega? Right. So I gave you guys the rest of the class. You guys got a solid 20-something minutes right here. Give you guys the rest of the class. You guys work on this page today. And again, we'll save the back half of this page for a different day. Okay. I'll walk around, troubleshoot any questions you guys got. And make sure you guys are doing all right.